There is a slight change in the agenda. So unfortunately, Dr. Thomas Kolbe, who was kindly providing a presentation for this, he's having a bit of flu. So hopefully it is not anything too bad. But instead of him, we have Dr. Tatjana Kutzner, also for Technical University of Munich, and she can do the presentation. So welcome everyone, and we will start our webinar for today. So Tatjana, the floor is yours. Thank you.
So yes, okay, good. So I'm Tatjana Kutzner, and I work at the Chair of Geoinformatics as scientific research assistant. And so I will give you today an introduction to city modeling with CityGML, and I will also give some insights into the new version on CityGML, but mainly it's a general introduction to CityGML and how you can use it for city modeling. So when you have a city, then usually a city is a complex system that should be represented by a model, and usually in the city system you have various areas, you have actors, stakeholders, citizens, you have entities, all the city objects, other resources and processes, and all these things interact and have relations with each other. And to really understand the interactions, all these things should be represented by a model. So however, currently, when you look at your city system, you have separate sectors. You might have an energy sector, mobility sector, ecology, economy, also other sectors. And these sectors are modeled separately. You have your individual communities in all these sectors. You have your individual models. You have indicators. You have methods to evaluate or to measure these indicators. You have planning tools, and everything is separate. And to really understand the city system and all the interactions, it's necessary to link all the models with each other so that you get a lattice of models, which however is difficult to manage. And when we look at this lattice of sector models, then you see that every model is connected to each other sector or to each other model, and you have lots of connections. So with n sectors, you have n to the power of 2 connections, which makes it really difficult to maintain everything, to express everything. And a better solution would be to have one common model, a city system model, to which all the individual sectors are connected. And then you have much less connections, and you can manage things much better. However, to be able to align the individual sectors with the common city system model, you need a high degree of coherence between all the individual models so that you really can make use of all the individual information in the sectors within your city system model. And then when you have this common model, then your city system can easily be represented by this model. And then, so we have to look what are candidates for such an integrative model. And then here the semantic 3D city models come into play. So we have to look at our world from a spatial semantic view. So we have in our urban cities, we have many physical objects, and these physical objects occupy space in our real world. And then we have to look how we can partition this real space into discrete objects. So we have to decide what kind of criteria can we apply for such a partitioning. And the most obvious would be to make a thematic classification into different topographic elements. like for example, a separation into buildings, streets, trees, tunnels, bridges, and so on. And so the important thing for us is also then not to only represent the geometry of these topographic elements, but also to represent the semantic information, so that we can classify the objects with a thematic data, with thematic information, and also represent the spatial aspects like the location or the shape or the extent of all these objects. And then also it's important that we represent all these objects in different levels of detail, depending on what kind of application you might need more detailed information or more detailed look on the models, or sometimes also a more general view on the models is, on the objects is enough. And since the real world is in 3D, also our city models should be modeled in 3D. So and this means that we can decompose our urban space in a 3D way into meaningful objects, and the object should have a clear semantics, and they should also define spatial and thematic properties, so that in the end we end up with objects like buildings, roads, railways, but also water bodies, vegetation, and so on. And then these objects can be decomposed further. So for example, buildings could be decomposed into different stories, or even also in apartments. And then also we can also apply data, application-specific data with these objects. And one way to represent the 3D city models is CityGML. CityGML is an application-independent geospatial information model for semantic 3D city and landscape models. CityGML comprises different thematic areas, so we can represent buildings, vegetation, bridges, terrain also, or the land use of the areas. And in CityGML is on the one hand defined as a data model, for which we use the unified modeling language. And CityGML is also an exchange format, which is based on GML3, so that we really can also exchange 3D city models in a data format. We have 3D geometry, we have also 3D topology, and so we can attach semantic information to all the objects, and we can also attach appearance to the objects. And then we have here 5 discrete levels of detail. So we can represent objects just maybe as a block model without roofs. We can also represent roof structure then, or windows, so depending on what kind of level of detail we are interested in. And CityGML is also an international standard of the OGC. So the current version is CityGML 2. And so since a few years we work on the new version 3.0, which should be released early 2021. So currently the new version is going in a review within the OGC, and then there will also be a public commenting phase, and then early 2021 should be ready to be published. So here we see several application areas for which CityGML can be used. So for example, here for radio network planning, when you want to find out where the best position for a transmission station is, you can also do noise emission mapping to create noise maps to see which maybe streets are quite noisy, or yes. And for example, also in urban planning, you can use CityGML. You can do facility management with CityGML, and also other areas where you can use CityGML. Also in simulators, for example. And so there exists already a lot of city models. So here's an example for the 3D city model of Berlin. This 3D city model has been also modeled using CityGML. There are more than 550,000 buildings, and they have all been automatically generated from 2D cadastre footprints and from airborne laser scanning data. All the buildings also have textures attached so that you really have a quite realistic impression of all the buildings. And also semantic information is also provided for the objects. And also utility networks have also been modeled in Berlin, like here, electricity, gas and water networks. And there's another example for a 3D city model in New York City. This city model was created using open data from the New York City Open Data Portal. And we did this with master thesis. So we had 2 master theses some years ago where we created a city model in CityGML from New York City in LOD 0 and 1. And the Open Data Portal provides a rich set of semantic information, which we can then attach to all the objects. So we have represented more than 1 million buildings. We have many landlots. We also have represented streets, parks, and water bodies. So it's a quite comprehensive city model. And this is also available for download. And so another advantage of CityGML is also that you can integrate application-specific information with your objects. So for example, here we have a building object, and then we can use this object for various applications, like in the energy domain, estimating the heat energy demand, and the results from these estimations can then also be attached to the object for further use, or also in noise emission. You can estimate the noise levels on the facade, and yes, and so on. And in this way, you can use 3D city models also as integration platform. So this means you have your 3D city model, which can be used in a wide areas of application, like in cadastre or mapping, in urban planning, real estate management, navigation. And in all these areas, you might also perform analysis, or based on the information you have in your 3D city model, you might create new information, which then can be fed back into the city model. So, and this means so that you can enrich this 3D city model with further information, which then can also be used in other areas again. Yes, so CityGML is used internationally. So, for example, also in Germany, almost all German cities have 3D city models. Then, of course, we have a 3D city model in Helsinki, Rotterdam. So in Europe, quite many, Paris, for example, but also Vancouver has a 3D city model. Then in Asia, Kuala Lumpur, for example, or also in New York, the 3D city model. Many mapping agencies provide 3D city models in Germany, France, in the UK also. And also in the Inspire initiative, there is a Inspire building model, and this building model is also based on CityGML. Yes, so next I would like to give some details on CityGML. CityGML is a modular standard, so that means we have here at the bottom in red thematic modules, and these thematic modules define the individual objects we have in our urban landscapes. So for example, the buildings are defined here, bridges, tunnels, also city furniture, like street lamps or banks where you can sit on can be represented. Then also the land use of your areas. You can also provide digital terrain models with the relief module. We have the transportation module, about which we will hear later on more by Christof Beil. Vegetation, so we can represent trees, for example, and also water body for representing rivers and lakes. And then we have a construction module also, which can be used to represent constructions like dams or wind turbines, chimneys, and so on. And then we have the more general modules in blue. These provide concepts that are applicable to all thematic modules. And on top, we also have a core module, which also provides base concepts for CityGML, and also geometries are defined there. And so, for example, here we have 4 modules which are new or which will be new in CityGML. We have a dynamizer and a versioning module. These modules can be used to represent dynamic behavior in city models. I will explain a bit more about this later on. We can also now represent point clouds. So all city objects can also be represented as point clouds. And here this construction module is also new, which allows us now to represent other constructions like dams or wind turbines, chimneys in a better way. And we also revised some modules. So the building module was revised a bit. We can also now represent building subdivisions in a better way, like stories or also building units. And also the transportation module, which will come in the next presentation. Okay, so this just gives you again an impression or idea about how we do thematic modeling in CityGML. So we have all objects are or represent city objects in GML, and all these city objects are then part of a city model. And the city objects can be then the thematic objects like the buildings or the transportation objects, the vegetation, trees, and so on. And all objects can also be linked to an external reference. So for example, to an external information system. For example, you have information on an object, maybe in the cadaster or so, then you can link your object to this cadaster. And we also see here that all objects have a geometry, and we can represent the objects in various geometries and various level of details. In CityGML, we have, so at least up to now, until version 2, we have 5 levels of detail. Level of detail 0 is usually to represent a regional model with a 2D dimension. Then we have this block structures in LOD1, more detailed structures with roofs, for example, in LOD2, and then windows and detailed architectural models in LOD3. And in LOD4, up to now, we have indoor representation of models. And this is something we will change in CityGML version 3. So this means we will only have 4 levels of detail in CityGML 3. The level of detail 4 will be removed, but it will be now possible to represent the interior of the objects at every level of detail. So this gives you also the possibility, for example, to have floor plans of buildings in level of detail 0. And it also gives you the possibility to mix levels. So for example, you have a building where you are more interested in the interior representation, then you could use for the interior part LOD3. But for the exterior, you could then just use LOD1. And also this gives you the chance to use city models in applications, for example, also for indoor navigation or also energy applications. So CityGML itself represents a core or defines core concepts for the city, but for various areas of application, it's often necessary to extend CityGML. So on the one hand, we have the strict core with all the modules I've shown before. And this data model consists of well-defined classes. Then we have two extension mechanisms. So we have something that is called generic objects and attributes. And this allows you to simply add information to your data sets. So this is something which is not in the, which you do not define in the data model, but you simply add this additional information to your data sets. And this is something we call extension during runtime. So you do not need to modify the schema. And then we also have a systematic extension mechanism, which is this ADE mechanism. So ADE is short for application domain extension. And this really allows you to extend the data model to define new objects or to define new attributes for existing objects. And so there are many or a lot of ADEs that already exist. For example, there's the energy ADE that can be used for doing energy simulations. We have the utility network ADE, which allows you to represent utility infrastructures like electricity networks, water networks, and so on. And there's also the noise ADE, which you can use for noise mappings. So new in CityGML 3 will be the representation of dynamic behavior in 3D city models. So we have to differentiate between slow changes and between highly dynamic changes. And highly dynamic changes, for example, are variations in spatial properties, so that can be that the geometry of a feature changes. For example, when you look at moving objects here, the location can change quite fast. Then also thematic attributes can change, like the energy demand or the solar irradiation on a wall can change quite fast. Then also appearance, when you have raster images that show the air quality, they can change. Also here in the image below, there was a fire on this building, and then you could attach different images showing the different stages during this fire onto your building. And you can also have variations in sensors or real-time data when you have sensors attached to your city objects. Like for example here, the heating demand of buildings, which varies here during the hour and also during summer and winter. And we introduced a concept called dynamizers in CityGML 3, and this allows you to link feature properties with time series data. So you have your city objects on top, like for example here the buildings again, and the buildings, they have spatial properties, geometries, they have thematic properties, and they also have appearance properties. And then at the bottom you have sensors, for example, a sensor attached to your building wall that measures the solar irradiation on the wall. And this sensor provides real-time data. You might also have results from sensor information or results from simulations stored in databases or external files. And with the dynamizers, these dynamic information can be attached to the spatial properties, to the thematic, and also to the appearance properties. So there is an example here how this would work. So we have here our wall surface on the left represented, and this wall surface has an attribute called global red month, and this provides you information on the global radiation for every month. And this usually is a static value, so you can only provide one value with this attribute. And then on the right, you have simulation results that show you the radiation for every month in a year. And then we use this dynamizer object. And this dynamizer object here, so we say what is the start time and the end time of our simulation results, and we reference then, yes, and here below in this dynamic data, we provide here the simulation results, and we say then that these simulation results should replace here on top this static value. And then also using this dynamizer, we can then also represent these simulation results with the city model. So here is an example from a project we had also. When you click here on the wall, then here the radiation is shown for every month. And then also we not always have only fast changes, but we could also have slow changes. So for example, when we look at the history of our city, how is our city evolving over many years, or how, or if we want to do urban planning and want to maybe look at parallel versions of a city at the same time. So these would represent slower changes. And for this, we introduced the versioning module. So this allows us to explicitly model slow changes, to represent snapshots of a city model at a specific point in time. So we could then have a snapshot here of Singapore in the year 2000. And we could also have a snapshot now at this day. And so all objects can have bitemporal lifespans data. So we provide the date when the object was created or demolished, and also when it was inserted in our city model. And this allows you then to answer questions like, how did a city look at a specific point in time, or how did the city model look at a specific point in time? And then also we can represent multiple versions of city objects within the same city model data set. So next I have a few application examples for which we used CityGML in the last few years. One example is for energy simulations. So in Berlin there was a project called Energy Atlas. The same was also done in London. And this Energy Atlas was created as a tool for holistic energy planning. So the tool should be used for analyzing and representing the state of objects together with their energy relevant parameters. And the tool should also be, or it should also be able to use the tool then for doing analysis of options and measures, whether these options are useful or not. And then also should support in decision making for various actions and also for visualizing the results. And also the Energy Atlas Berlin serves as information backbone then for multiple analysis and simulations. So we can do estimation of heating demand, of electrical warm water energy demands. We can also estimate the rehabilitation potentials, for example, and also design an optimal electricity network, taking into account the current demand and load peaks. And we could also use the information for estimating geothermal and solar energy potentials. So usually, there are several scale levels you have to take into account. So there is a city level, district level, quarter, building, down to the room levels. And so the more you go downwards, the more detailed the information becomes. So the level of detail increases. And in contrast, in the other way, when you go more upwards, then the information needs to be more aggregated. So for example, for a person which is more active on the political or entrepreneurial level, where you have to solve strategic goals, then you would be more interested on information on a city level, which is more aggregated. But on the other hand, an engineer which really looks at how to make a building more energy efficient or so, then you need a more detailed level, and you would look more on the building level. Yes, and then this energy atlas was used here for energy demand estimation. So usually for energy demand estimation, you need consumption data for electricity, water, gas, but this information is rarely available because due to privacy issues, so the companies do not easily give you all this information. On the other hand, you have all the building data available in your 3D city model. You have information on the volume of the buildings, floor space, for example, the building type or the year of construction, the number of inhabitants, and then you would try to estimate the relation. So what the amount of consumption based on specific building characteristics. So you try to define a specific correlation function here. And then when you have this correlation function and all the information from your 3D city model, then you can estimate the energy demand for every building, but also you could then aggregate these energy values and then estimate also the energy demand on a district level, for example, or also on the city level. And then when you want to apply measures or just want to see whether these measures would be useful at all, then you can apply these changes to your city model, and then you can directly compare the results of your changes with the current status. Yes, so and for the heating energy demand in Germany, there is a German standard which provides you formulas for how to estimate these energy demands on a building level and also on a city level. And then, so for example, for the heating energy demand, then you would only need to use information on the building geometry, the building usage, the construction level, and then with this correlation function, then you can here estimate the energy demand and also do all your analysis. And here, for example, this green building here, this is from our city 3D viewer. So when you click here on a building, you get here then all the information on the energy demand for every month in a year. And then when you apply your insulation here on this 3D city model, then you could directly get the results for the refurbished, or the results when the building would have been refurbished. And based on this information, then you can decide whether the refurbishment, for example, makes sense. Yes, and this can also be done then for districts. So you would then aggregate the results from every building, and then for here a small village, I think, or no, it's a part of Berlin. Here, then you would get, for example, information on this, I think was for solar potential analysis. You would then get here the area, the available area for installing photovoltaic. And also you would get information on how much heating energy this yes, would save. Yes, so that's how you can aggregate these informations. And then also the energy atlas. So here for the energy atlas, the energy ADE was used, and also the energy ADE was also developed or further developed as part of this project. And the energy atlas can then also be used for geothermal potential analysis or solar potential analysis and other things. And also the results from all these analyses can then also be fed back into the energy atlas. Then another example is on simulating critical infrastructures. So we have an ADE called Utility Network ADE for representing supply infrastructures, and this can be used for simulating cascading effects between different infrastructures. So for example, here in this distribution station, there was an explosion that caused a power failure. You do not have streetlights anymore in your district. And this power failure would here cause also a failure in the water supply, because close by there is a waterworks. And this means you have a cascading effect which goes from one network to another network. And then based on, so you can then calculate how many people are affected by the power failure, how many people are affected by this water supply failure. And then you can, yes, estimate maybe how many people would need to be supplied with fresh water, for example. And then you could supply the water to them. So the problem currently, however, is that the utility companies, they manage the different types of networks independently, and this makes it difficult to simulate these cascading effects. And with the Utility Network ADE, we can represent multi-utility networks in an integrated way, and also integrated with semantic 3D city models. So we developed the ADE in such a way that we can really have connections between the networks and the buildings, so that we really can see, okay, there is a failure in this network, which buildings are affected. And also we have a connection between different network types. For example, this water pump here represents or connects the water network with the electricity network, so that we can really do this integrated modeling of networks. Then another example, so on a vulnerability analysis. So some years ago already there was, so we still have these bombs from Second World War sometimes appearing when you have construction works. And one of these bombs, so it was not possible to defuse this bomb, so it need to be detonated in a controlled way. And so it did not turn out as expected. So there was some damage to some buildings close by. And then afterwards, we made a project where we tried to simulate this bombing. So also using a city model, and then, so you can see this here in this image, then you can really simulate how this explosion wave propagates and which buildings might be affected and which areas, yes, might be affected, or from where people need to be evacuated to be on the secure side. And this is also something that was used, I think, in the beginning of this year, also somewhere in Germany, there was also a bomb. And then, for example, the company Virtual City Systems, they used this tool also there now, previous or before the detonation in front, to really simulate beforehand which buildings might be affected. So, so this was some, yes, insights into 3D city modeling, CityGML, and in which areas we applied CityGML. Now, just to wrap things up, so semantic 3D city models are an appropriate reference model and data platform to link urban information from various areas of application to the platform. So to really link, yes, information and connect information from various areas of application. Semantic 3D city models are often provided by authoritative sources, so by many mapping agencies, so which means that you have a full coverage of the urban space for many cities, but also for the whole country sometimes. And this gives you highly reliable and stable data sets. So in contrast to 3D models or OpenStreetMap data from Google, you also really have a 3D representation and you have a semantic representation. So with Google or 3D models, you only have a geometric representation, but no further semantic information that can be used for analysis. And in this way, so 3D city models then can be used for analysis on the urban scales in many fields like energy assessment, environmental simulations, or urban planning. And also you can accumulate the knowledge. So you can do analysis and then you can include the results in your 3D city model. And so for an integration of all this information from the various applications, interoperability is required, and CityGML is, I would say, the standard that gives you this interoperability, because it defines the semantic data model and also an exchange format. You can also extend it with ADEs, and CityGML is also an open and vendor-independent standard. And you can do 3D visualizations with CityGML, but you can also use it for thematic analysis, which I think is the very important aspect for CityGML. And the new version, CityGML 3, so was designed in such a way to improve the support for various applications, so also in urban planning, in energy simulations, but also in traffic analysis and autonomous driving, and also in the context of smart cities. Also by now linking dynamic data, sensors with our city objects. The new LOD concept, so with the possibility to represent interior in every level of detail, gives you also more flexibility in representing the indoor and outdoor world, and also representation of objects by point cloud is also a new feature. Then something which I did not tell up to now. So for example, by revising several modules, we also provide now a better interoperability with other standards. So indoor GML is a standard for indoor navigation. So this can now also be linked in a better way with CityGML. Also the IFC standard for building information modeling. So there's a better way now to map IFC datasets to CityGML. Also the land administration domain model. We have better interoperability also with Inspire. We simplified geometry handling, and so we improved the representation of our physical and logical objects. And now also with the new version, we applied, or we ensured that the UML model is compliant to all the current ISO standards. And so this gives us also the possibility to derive exchange formats automatically using shape change. So we do not do this manually anymore. We simply shape change reads the UML model and creates GML application schemas. But later on, we can also then create other exchange formats like JSON, for example, or database schemas. But so we have to wait until the beginning of next year for the final voting of CityGML 3. So there are some references also. I'm not sure whether the slides will be provided later on. I collected some references, so there is also a paper on the new CityGML 3 model, some papers on the dynamic modeling, also one on the utility network ADE, and an older one on the energy atlas. Okay, thank you. That was my introduction to CityGML.
Thank you. That was very interesting, and it is a great opportunity to really go through the whole thing, because we all have seen so many 10-minute or 15-minute presentations that only touch the overview. I think, well, we have one question. Patrick Okko is asking, where can be found more info on better map between IFC and CityGML? Well, that is
okay. So in this paper, in the topmost paper here, CityGML 3, there is a short section also on mapping IFC to CityGML. There is also a GitHub workspace where we provide a small FME dataset where we read an IFC model and yes, map it to CityGML. So apart from that, I would have to check if there are other papers. So.
It's also a topic that there are of course two things. There are the standards, but there are also the conventions, how they are being using. What is your view at the moment that which side is the bigger problem in the interoperability or conversions from IFC to CityGML? Is it the standard itself, or is it just the using conventions of the IFC models?
I think it's the standards, also the way of representing geometry. So in IFC you have the volumetric objects, And in CityGML, you have the boundary representations. And I think this, for example, is a huge problem. And then also the, how to say, the reference systems. So in CityGML, you have so in BIM, you have this, or I've seen these local reference systems. And then in CityGML, you have your objects located on the earth in the real position. And this mapping is also difficult.
Yeah.
So I think there are difficulties in both ways, but for a better way to solve difficulties with geometries or with these volumetric representations, we introduced a new concept in CityGML so that you can really use your volumetric objects and also represent them as volumetric objects in CityGML.
Okay, thank you. Next question is about the wedge station and green infrastructure. Do you know if there are any application domain extensions that are related to the wedge station and green space in general, I think? Yeah, so I think there was a new paper from Singapore about the microclimates done on top of the wedge station object.
Okay, so I don't know about this one. And I'm also not aware of ADEs. So I just remember there is a paper from Philip Bieletsky, which gives an overview of all kind of ADEs that currently exist for CityGML. So I could also provide this link.
Okay,
or I can write it later in the chat window, maybe.
Yes, good.
For it.
Thank you.
And maybe in this paper, maybe there is some information on vegetation. ADEs.
Good, thank you. Third question is about how do you get the energy data for the models, as an example in the Berlin case or in the London case, if you have energy ADE.
Yes, so for the Berlin case, I know, so I was not involved in this project, but the project was in cooperation with many energy companies, and they provided all this information then. So yes, as part of a project, then it's more easy, but usually it's difficult to get the information. Yes.
Okay, thank you. No more questions from the attendees, but I would just like to add one more question, and that is about your research at the moment. That of course the team has been quite busy with the CityGML3 in the recent times. But what kind of research topics do you have at the moment in relation to the CityGML in your team?
So one topic is, of course, the transportation topic, which Christof will tell about, but we also do solar potential analysis. We do, what else are we doing? Yes, transportation, I think, is a big topic. Also, another colleague is working on this, on autonomous driving. So we have a project where, together with Audi, where we also represent or use CityGML then in autonomous driving. That is a topic. And yes, I think.
Yes, and I will present some of the models, some of the applications, and some of the demos shortly, at least for transportation.
Good, excellent. So this was a good bridge to the next one. So Christof Beil, also from the same unit. Well, floor is yours.
Now, yes, great.
Thank you.
So you should see the first slide of my presentation, right?
Yes.
Yeah.
Great, okay. Thank you very much. And hello, everybody. My name is Christof Beil. As already mentioned, I'm also a researcher at the chair of Geoinformatics at the Technical University of Munich, at the chair led by Professor Thomas Kolbe. And my field of research is mainly in the area of street space modeling in the context of semantic 3D city models. And I want to present to you some of my and our research on detailed street space modeling with CityGML and show you some of the applications for this. I've structured the talk in the following way, so I want to show you quite a lot. First, I want to start by introducing the topic of street space modeling in the context of city models to you. I want to give you some background information, why this is important and why this is a topic that's getting more and more relevant. I want to show you some potential applications for street space models in the context of city models. I want to also briefly introduce to you some related standards, because obviously there are already applications for street models for navigational purposes, for traffic simulations and so on. And there are existing and established standards that provide a number of concepts, and I want to briefly introduce those to you. And then I want to have a more closer look at CityGML 3.0 and especially the CityGML 3.0 transportation model. Tatjana just mentioned that this model was revised and extended, and I want to show to you some of the most relevant and interesting concepts concerning representations of semantics, geometry, topology, and appearance. We heard a little overview on that already, and I want to specifically show to you how CityGML 3.0 transportation model covers these aspects. I also want to show to you how an integration of multiple transportation types is possible with CityGML, and I want to give some examples on potential uses of the application domain extension concept we already heard in the context of transportation-related purposes. And then in the main part of this presentation, I also want to show to you already some demos and applications and examples, since there are already some street space models available. The biggest part of that will be the presentation of the model of New York City, which was generated entirely from open data. But there are also other models available for different cities, including Melbourne, which was also generated at our chair from open data. A model of Grafing, which is a small town near Munich, which was generated from drawing data, and a street space model of Ingolstadt, a town in Bavaria, which was generated from OpenDrive data. So you can already see that there is a number of examples for street space models available, and there are different ways for generating these street space model depending on available data. And I want to present this to you today. So, short introduction to this topic. Spatio-semantic representations of street space are getting increasingly relevant, and this is due to several factors. First, highly detailed data is more and more available, so for example from mobile mapping systems and so on. And second, there are emerging applications such as digitally testing autonomous driving systems that need this information. And these applications depend not only on geometric, but also on semantic and topologic information, as we just heard, and also need georeference data for a large scale. And as we also just heard, semantic 3D city and landscape models can provide this information and also serve as a foundation for these applications. We heard also that CityGML is one of the most commonly used data standards, data formats or standard in this context, and is often used for modeling, storing, and exchanging 3D city models. And this is why I want to present to you also the transportation model in this presentation. I just said that there's an increasing interest for street space models, for example, from the automotive industry, for testing autonomous driving systems, for testing driver assistance systems, but also from urban facility management, for example, for applications such as road maintenance, for environmental simulations, 3D catasters, and so on. And I also just said that there are data registration techniques that can acquire this highly detailed information, but there is so far not much experience on how to subdivide and structure this road space elements in the context of city models in order to make the data usable. So the question is, what semantic classes, geometrical and topological properties or relations between individual objects are required in order to be usable for as many applications as possible? Until now, city models mainly still focus on models of buildings. I think LOD2 models of buildings are quite common now, but other parts or thematic parts of city models, such as transportation objects, are not that have played a minor role so far. And there are other data models available, but they often only are tailored towards a specific application. They support, for example, navigational applications, or they are intended for planning and construction applications. But there are very little standards who can cover multiple of these applications. Additionally, most of these standards, other standards, focus on linear and parametric representation and not on explicit representation of aerial surfaces. And I will show you in a minute what this also means. CityGML2 already comes with a transportation model, but now in CityGML 3.0, deficits have been overcome with extended and revised concepts. Here are some potential applications for street space modeling. One big sector might be infrastructure planning and management. For example, if you have aerial information on streets available, you can do calculations on areas, on pavement conditions, and so on, and do spatial calculations with this in order to have information on maintenance applications, for example. The next big sector might be the automotive industry, where street space models can be relevant for testing driving dynamics, for driving simulations, driver training, traffic simulations, or also for autonomous driving. Autonomous driving can be, for example, tested virtually, and you'll need so-called HD maps for that, and detailed street space representations can serve as a foundation for this. A third area for potential applications of detailed street space models are classically spatial analysis applications such as visibility analysis, or also solar irradiation analysis for locating urban heat islands, for example. And you can see an example here, which I will show you later. We have already done tests for solar irradiation analysis also for street space objects, and I will show you this later on. When developing the new concepts for the CityGML3 transportation model, we first, or during this process, we always had a look at different related standards and data formats. So I've listed here a number of data standards and formats that are relevant in the context of street space or transportation modeling for different applications. For example, geographic data files, GDF, is a format commonly used in navigation. OpenDrive is a format very commonly used by different automobile manufacturers, Audi, BMW, and so on use this format. OpenStreetMap can be used for representing street objects. And there are other less common or less known formats, for example, RoadXML, which is quite similar to OpenDrive. And of course, also industry foundation classes has, for example, the possibility to model street objects using IFC alignments. There are current developments for an IFC road going on. So all of these standards have their own concepts for representing street space. And we found that most of these standards focus on either a linear representation for streets or a parametric representation of streets, where a center line is used, a reference line, and information on different objects is stored parametrically. CityGML, on the other hand, is a format that allows explicit aerial representation of streets, which can be beneficial, for example, if you have changing street widths and so on, and to represent markings, sidewalks, plazas, and many more. And so we compared these standards and tried to learn from them and ensure interoperability between those different standards. I will not have the time to get into detail in this table, but in our recent publication, we checked all of these different standards for several aspects. So we had a look at how geometries can be represented, how semantic aspects can be represented, which topological concepts are integrated, and if it's possible to have models using appearance textures, for example. So as you can see here, all of the standards we had a look at obviously allow streets to be represented with straight lines, but if you want to have a more accurate representation using splines or clothoids, for example, then there are already some standards that don't support this. Aerial representation, explicit aerial representations, is also not supported by all of these standards, and if it is supported, then there are often no concrete concepts on how to do that. The standards we had a look at mostly focus on a parametric representation, and yeah, that's one of the findings we had. We also had a look at different semantic capabilities of these standards. For example, all of the standards, unsurprisingly, allow a representation, for example, of surface materials or different functions of traffic surfaces. Not all standards support representing street space in a lane level. For some standards, it's only possible to represent the entire width of the street, for example, by a single center line, for example. Then street space does not only consist of the streets itself, but also on objects that relate to this. For example, bridges, tunnels, road markings, street furniture, vegetation, and so on. And this is one of the advantages of CityGML, since all of these objects can be integrated in a common model, but most of the other standards do not focus on these objects and have no concepts for integrating these. Also, linear referencing, we had a look at that. This again is supported by most of these standards, since, for example, OpenDrive or RoadXML are mainly used for driving simulation. We also put into the table the main application of each standard and who developed the standard. We did the same thing and checked for combining multiple transportation types. Also, I cannot go into much detail, but we also had a recent publication on this topic where you can find more detailed information. We had a look at, is it possible not just to represent roads, but also railways, bikeways, tramways, busways, and so on, in combination of that, for example, level crossings. And you can find this table either on the corresponding website or within the publication. And one of the big advantages of CityGML 3.0 will be that CityGML offers concepts for a consistent and integrated representation of multiple transportation infrastructure. And I also want to explain this a little more in this presentation. So we did a comparison of these relevant standards and data formats. And obviously, these standards are tailored towards needs of their intended applications. We tried to learn from this, but CityGML does not intend to replace these standards. But the existing formats have obviously some elaborate concepts, and there's data and software available, and it's important to have an interoperability between those standards. So it was important to have a look at these standards when developing the new concepts of CityGML 3.0 transportation model. And CityGML and city models, as Tatjana already showed you, has the big advantage that you can link different domains with each other, and thus it is important to have interoperability. This would be my short introduction and background information on the topic. And now I want to show you some concepts of the new CityGML 3.0 transportation model in order to better understand in the following the examples and demos and applications I want to show to you. So I don't have to talk much about this. Tatjana just gave you a detailed introduction to CityGML in general, what it is used for, and some of the concepts that are within CityGML. And she also mentioned that the next version 3.0 will be available shortly and is subject to final voting in the very, very near future. So I want to get into more detail on the transportation model. You've seen this graphic before. CityGML obviously contains many different thematic aspects. And one of these is the transportation module, which was extended, revised, and some of the concepts I want to show to you now. Yeah, that's what I already said, revised and extended concepts. You can find the conceptual models, not just on the transportation module, but on CityGML 3.0 in general on a corresponding GitHub page. So if you're interested, follow this link. I think we will provide the presentation after the presentation. So this is what the UML diagram or the conceptual model of the transportation model looks like. This might look a little intimidating at first, but I'll try to guide you through this step by step. First, let's have a brief look at those four main classes. It is possible to model tracks, roads, waterways, or railways within the transportation model. Tracks would be small paths, mainly used by pedestrians or bicycles, for example. Roads are ways mainly used by vehicles, but this also includes sidewalks directly next to roads or areas directly next to roads within the transportation space, so to speak. A new class in CityGML 3.0, which was previously not available, are waterways. So it is now possible to model routes of vessels or ships or ferries upon a water body. Railways have been there before, and they can still be represented with CityGML 3.0 for representing train or tram structures, for example. So what I want to focus now on the road class. Now highlighted are the most important classes concerning roads. And let me just restructure these classes to tell you what they intend to mean. Roads can be partitioned into individual sections and intersections, and individual sections and intersections again can be split into traffic areas and auxiliary traffic areas. And within the next few examples, I want to show you and demonstrate you this concept. So let's have a look at a very basic and simple transportation network. Transportation networks do have the disadvantage when you want to model them that they are quite large and extend through a whole city, for example. And we wanted to find a concept for segmenting this network into smaller parts and smaller objects. And one of the new segmentation methods or concepts we introduced is the introduction of sections and intersections. So you can see in this example, highlighted in blue, that sections are objects that belong clearly to one road. This can be a road segment, for example, a dead end like this. But this also applies for railway or track or waterway segments. The counterpart to this are intersections, now highlighted in orange. And these are objects that are belonging to multiple roads at the same time. For example, a three-way intersection, a four-way intersection, but also roundabouts and so on. And this concept can also be used for modeling level crossings, so an intersection of a road and a railway, for example. There's also a concept in CityGML for allowing a non-redundant geometric and semantic representation. So one of the things with intersections is that they can be shared by multiple objects. So in this case, there's road A and road B in orange, which share this roundabout highlighted in purple. And there's a linking mechanism within CityGML, for example, the X-link concept, which allows the linking of an object to several other objects. So in this case, there exists the object road A and the object road B, and both are linked to intersection M, what it's called in this example. So the intersection is represented geometrically only once, but both objects have a link to them and reference them. This way, this shared object doesn't have to be represented multiple times, but can be represented in a non-redundant way. I already said that sections and intersections can be further segmented into traffic areas and auxiliary traffic areas. You can see an example here. A traffic area would be an area, for example, a sidewalk or a traffic driving lane used for transportation or for pedestrians, while auxiliary traffic areas are areas within the context of a road that are not intended for traffic. So, for example, green areas in this example. Also, curbstones are declared as auxiliary traffic areas. And all of these different areas can have different class, function, or usage attributes. So for example, this traffic area would be declared with a CityGML function footpath in this example. Let's have a more realistic real-world example. So in this case, you can see in orange here a road A, and in blue, intersecting this road, road B. How would this be modeled? You could subdivide and segment this very small network into section A1 and section A2, which are part of road A, and section B1 and section B2, which are part of road B, and intersection AB, it's called in this example, which would be part of road A and road B at the same time. In the next step, each individual section or intersection can be split even further into individual traffic areas, for example, individual sidewalks, individual driving lanes, and so on. So each traffic area would be linked to the section it belongs to, and each section would belong to a specific road, while intersections can belong to multiple roads at the same time. There's also a new space concept in CityGML 3.0, which allows the mapping of all city objects to spaces. And this also applies to transportation spaces. And you can see a very simple example here, where traffic spaces are highlighted in blue. For example, in this case, traffic space is the space where the traffic actually takes place. So for example, the pedestrian movement or the vehicle movement in this case. Traffic areas are used to model the ground surface of each traffic space, highlighted in yellow here. And it is also possible now in CityGML to model clearance spaces, to model the free space above a traffic area. And since these concepts apply to indoor as well as outdoor objects, for example, indoor objects such as rooms can also be modeled as spaces. This allows a seamless transition between indoor and outdoor spaces, which is also an advantage of CityGML 3.0. I want to quickly show a short video on that. We manually digitized an orthophoto and created different traffic areas from this and textured these objects with the orthophoto, as you can see here, and each individual surface has some different functions contained, for example, a sidewalk attribute in this case. That's what it would look like if it's not textured, but colored by different functions. For example, in red here are biking lanes, blue are driving lanes, green are sidewalks, and so on. And also multiple functions can appear, for example, in the pedestrian crossing that is used by pedestrians and cars at the same time. And what we did here, a very basic, simple example, is we extruded all of these traffic areas in order to get the traffic spaces, for example, for driving lanes by 4.5 meters in this example, or for sidewalks by 2.5 meters. And this demonstrates the basic idea of traffic spaces. And this could then also be used, for example, in combination with vegetation objects in order to have a conflict analysis, for example, where spaces are used by different objects at the same time. There are also other classes available, which have been already available in CityGML 2.0. One of these is Square, which can be used for representing large sealed surfaces, such as plazas, in this example, or parking lots in this example. Those are both screenshots from the model of New York that I will present to you shortly. The section on intersection concept I just showed to you doesn't apply for squares, obviously, but a square can still, again, exist or consist rather from multiple traffic areas or auxiliary traffic areas. So this square could be made of a plaza area, as well as the sidewalks could also be part of this square, for example. A new explicit class in CityGML 3.0 is called marking, which is represented as an individual class. And markings should also be represented as additional surfaces to the street surface. So they are independent of any level of granularity, which I will explain later. And markings can also span over multiple auxiliary traffic areas. So it is indicated in this example that a marking should be rendered as independent object from the transportation surface above the transportation surface in this example. This is what this would look like for the model in Ingolstadt, which I will present to you in more detail later on, where the marking layer is represented explicitly. So you can hide this layer if you want to, if you're not interested in this. But you can still do, obviously, spatial analysis on areas, for example, if you want to know how much paint you will need to paint these markings, for example. An additional new class in CityGML is called Hole, which is an individual class representing roadway damages, for example, or manholes or drains. In this example, it's a manhole. This was also introduced newly into CityGML 3.0 for explicitly representing these kind of objects. Now I want to come to the next part and talk a little bit about the geometries used in CityGML. You can see here, and as we already heard that CityGML is based on the ISO standard 19107 when it comes to geometries, and these are the potential available geometries which are fully supported by GIS and spatial databases, and as we already heard, are defined in the core module, and all city features inherit these different geometries. So the two most important geometries in the context of street modeling are multicurve for the representation of linear structures. You can see here that also clothoids or elliptical geometries are now allowed, which was not possible in CityGML 2.0, for example. And multi-surfaces can be used for representing aerial representations of street objects. It is obviously part of CityGML to use coordinate reference systems, which can be defined either through an attribute or often a GML envelope is used for describing the coordinates reference system. Also, local coordinate reference systems can be used in order to support a better integration, for example, with BIM models. But we also heard a little bit on this before. So let's come back to street space modeling and how streets should be modeled with CityGML 3.0, I should say. In CityGML 3.0, we introduced a so-called level of granularity in order to allow a different thematic decompositions of street objects. There are 3 levels of granularity available. In the most basic level of granularity, the entire width of a section, for example, would be represented using just one object, while in the highest level of granularity, each individual lane can be represented. And as I already said, it's not only possible to have an aerial representation of street space object, but also to have a linear representation. And the same level of granularity concept applies here too. In the lowest level of granularity, the entire width of the street would be represented with just the single center line, while in the highest level of granularity, each individual lane would be representing using individual linear geometries, including pedestrian representations using line geometries in this example, for example. So let's come back to the previous example and have a look what it was looked like. In the lowest level of granularity, each section would be represented using just one aerial geometry or one linear geometry. In the next level of granularity, each individual way would be represented. This means that sidewalks used by pedestrians or pedestrian crossings would be represented separately. And in the linear model, there then would be a linear representation for the traffic, car traffic, for example, and pedestrians as well. And in the highest level of granularity, then the sections and intersections would be split into many different traffic areas, in this case, representing each individual lane. So for the aerial representation, this could look like this. And for a linear representation, this could look like this. Now I want to briefly introduce to you or talk about the X-link concept I mentioned before in order to be able to have a non-redundant representation. The X-link concept was also available in CityGML 2.0, but there it was mainly used for buildings. So in this example, you can see two buildings next to each other that share one wall. And using the X-link concept, this wall depicted in gray here would have only be represented geometrically once, and both solids would reference this, this geometry. So the geometry would only be represented once, but be part of both objects at the same time. And the same concept will be applied to road infrastructure. So for example, an intersection that can belong to multiple roads at the same time would be a part of multiple roads using this X-link concept. A new concept is also a predecessor-successor concept, with which allows or is intended to allow CityGML linear networks, or also it can be used for aerial representations, to be better usable for routing and navigational applications. So each traffic space can have information on its predecessor and successor, and you can see a very basic example here. The appearance model, we also hit a little bit on this. So surfaces in CityGML can have multiple representations, textures, and multiple appearances. That's what I wanted to say. And this also applies obviously to transportation objects. So in this example, you can see that the model here was textured with asphalt or concrete textures. And the same geometry could also be textured with results, for example, from a solar irradiation analysis. Now I want to briefly have a look at integration of multiple transportation types. So I said that these concepts do not only apply to roads, but also to railway or waterway infrastructure. And as you can see here, especially in bigger cities, those different transportation types do not just coexist next to each other, but often directly interact. So you would have here tramways or trains going through roads with level crossings, pedestrian crossings, sidewalks, and driving lanes, all within the same model. And CityGML offers concepts for an integrated and non-redundant representation of such scenarios. A very simple thing would be, for example, if you have different surfaces with different functions. For example, in this case, the surface highlighted in dark blue would be at the same time used by cars, thus labeled as CityGML function driving, as well as by pedestrians because it is part of a pedestrian crossing, and thus could have multiple function attributes. For a linear representation of the same scenario, one would have independent linear representations for the different transportation types. So in blue, this would be the driving network. In green, this could be a pedestrian network. And in red, it would be a representation for bike lanes, for example. It gets a little more complicated if you have a direct interaction of a road object with a railway object, as it is the case in this example. So But since everything is defined within a common standard, the section and intersection concept I just showed to you also applies to railways. So in this case, the road would be represented with section A and section B. The railway would be represented with section C and section D, and intersection E could be shared by both of these top-level objects, so to say. Again, same concept as I showed you before. Each section and intersection can be split into individual traffic spaces or traffic areas. But since these traffic spaces are clearly assigned to one intersection, for example, there are no redundant representations because both the road as well as the railway object are linked to this intersection, for example, via X-links, as I just showed to you. And thus you don't have to have the intersection represented twice, which may result in some problems, for example, when visualizing these objects or when doing aerial calculations and so on. The same also applies for the linear representation. I just highlighted here with small black dashes that it should be considered that the linear and the aerial representation should be consistent. So whenever an aerial representation would switch from, for example, a sidewalk to just the railway lane, then also the linear structure should be split at that point. But it is possible to have the same representation. Now I want to briefly introduce you to concepts for integration of transportation and building objects. So let's assume we have a transportation network split in sections and intersections, as I just showed to you, and here would be one dead end, which is a section leading to this parking garage house. Let's have a look at that building. This could be represented as a CityGML building, the entire thing, with floor surfaces and ground surfaces, as you might be used to from CityGML 2.0. But at the same time, using the X-link concept, those surfaces could also be declared as traffic areas. And thus, it could be linked to transportation areas outside of this building. For example, the section which is representing using a traffic area and an auxiliary traffic area for this green area. And so you could do navigational purposes using the predecessor-successor relations for traffic areas within the building. So this is entirely, is something new that I wanted to present to you. We already heard about the mechanisms for extending CityGML. For example, CityGML generics. This is also relevant for transportation infrastructure. For example, if your CityGML does not provide attributes such as speed limits or number of lanes or pavement conditions, which might be interesting for your application. With the generics, it is simply possible to declare these attributes or additional objects and integrate them within your model. Using the second possibility for extending CityGML could also be relevant for transportation objects by defining application domain extensions for different purposes. I talked about OpenDrive in the beginning, which is a very common standard for street representation, but the standard uses a parametric representation and also contains concepts on linear referencing, for example. And since this is not contained within CityGML and will also not be contained in CityGML 3.0, it could be considered to create a CityGML application domain extension for OpenDrive specifically, which is possible. And we already heard that there are some examples for IDEs in use. So that was quite a lot on background and concepts with CityGML. Now I want to show you some street space models, demos, and applications, how these concepts can be used and why they are interesting and might be relevant for digital twins, as well as classically semantic 3D city models. I want to first start by telling you that there are some CityGML tools available as open source. For example, the 3D city database, which contains an CityGML importer and exporter and allows the exportation of KML or Collada data, and also the creation of spreadsheets, which allows the integration of semantic information within the visualization model. And there is the 3D CityDB web map client, an extension to the CGM virtual globe, which allows the integration of multiple thematic layers and also the integration of the thematic information with the geometric information. This can be run on any web browser and operating system, including mobile mapping services, devices, sorry. And all of the examples I want to show to you in the following slides. First, you can visit them interactively yourself. And secondly, they are visualized and made available using these tools. I want to start with the CityGML street space model of New York City. We heard a little bit on this before. This model contains over 500,000 CityGML street space objects, which were entirely generated from open data and are combined with LOD2 models for the entire city. So you can virtually do a little sightseeing tour within the model. You can see here Madison Square Garden, Times Square, Broadway is represented, Columbus Circle, the Empire State Building, Central Park, and so on. And I want to show you some details of this model in the following slides. First, I want to show you how this model was generated. So as I already said, New York City offers very much open data on all kinds of topics and also on street informations. For example, there are street center lines available for the entire city. There are aerial 2D information on sidewalks, on driving lanes, on plazas, and many more. There are different data sets containing information on speed limits for individual streets, on pavement rating, and so on. And there's also a street design guideline, which contains information, for example, how high a traffic island should be built, and so on, which can be used for creating equivalent virtual objects. We used the software FME, Feature Manipulation Engine, to do the data transformation, manipulation, and integration, and created CityGML files from this. I have to state that most of the data created was still CityGML 2.0, but we created the data in such a way that concepts that are intended for CityGML 3.0 are already within this. So even though CityGML 2.0, for example, does not have sections, we split the individual objects in a way so that they could easily be transferred to CityGML sections once this is available for CityGML 3.0. As I already said, we created a visualization, and there are several publications available on this project. There's a project website where you can also download the data. There's an entire wiki describing detailed how the model was generated. And there's also a GitHub page where you can find all of the FME workspaces. I provided the links within the presentations, and you will see them within the next slides. So what were the challenges when creating the model of New York City? First, a proper segmentation of road polygons into street segments, sidewalk segments, or intersection areas had to be done, since not all of the data available as open data did this in the most sensible way, I would say. Then identification and assignment of elements belonging to the same road section was needed to be done. So a sidewalk lying next to a driving lane, for example, had no information that they are part of the same road. And these informations had to be transferred using different spatial or neighbor methods with transformers provided in FME. Then there were a lot of different thematic data sources. I said to you that there was information on speed limits, on pavement rating, and so on, but all divided over different data sets. We had to find ways to integrate this information within linking the information to one corresponding city object. We started with concepts of handling the third dimension. Most of the model is provided at base height 0, but we also integrated a terrain model for a small section of the model, and I will show you this soon. And of course, the large data volumes for the entire city of New York City were a major concern, and we had to come up with ideas how to handle this. You can find all this information on the project website. The link is put here. This is what the data source from the Open Data Portal looked like. So there is a planimetric database for the entire city of New York City, which contains polygons, for example, on intersection areas, on sidewalks, on roadbeds, on plazas, and so on. And as you can see here, for example, this sidewalk is one donut object, so to say. So we had to split this into 4 individual geometries and linking, for example, this sidewalk to the driving lane next to it, this sidewalk to the driving lane next to this sidewalk. And so we wanted to have the information which sidewalks belonged to which road, which was not within the original data. Some spatial transformations had to be done. This is what the centerline dataset looked like, and there were some, I call it simple scenarios, basic Manhattan and so on, which could be easily used, but there were also some rather complex scenarios with complex interchanges, with multiple lanes, one over another and so on, but only in 2D available. So we started by filtering the more simple cases and started with them, and then later had a look at the more complex scenarios. This is the basic workflow we used. We had center lines available, and they were also already modified within a project Tatjana we mentioned briefly before. We had these additional information on speed limit, pavement rating, and so on. And often there was a linking attribute, for example, a segment ID that allowed a transformation of this information into the center lines. The next step was then a spatial correlation of the information contained within the center lines to the aerial geometries provided in the planimetric database. And this then resulted in the combined model of aerial geometries with existing attributes and combinations with new attributes in this. This is what a very simple example on what these spatial correlations looked like. We had the centerline dataset, and in this case, the underlying road beds with aerial geometries. And you can see here in green, where a centerline could be correlated to a surface one by one, so to say. In this case, the surface under the centerline got all the information provided in the centerline, all the attributes, and so on. The orange example here, on the other hand, contains multiple center lines. So we had first a look how long are these center lines? Are they just overshoots here, for example? Then we would get rid of them. And once we could clearly assign the leftover center line to the underlying aerial geometry, again, we transferred the information from the center lines to the aerial geometries. In this yellow case, for example, you can't see this, but these are two center lines which are meet in the middle, for example, because those are two different street names, for example. So we had to split the aerial geometry at the point where the center line split and create two independent aerial geometries for the two different street sections, for example. So these are some very basic examples, but I just wanted to show you that it was not that easy to create the aerial model because information was split over different data sources and not always fit together perfectly. We also created individual traffic areas and auxiliary traffic areas from this, so individual road beds, sidewalks, and so on. And as I just said, we created objects according to the CityGML 3.0 standard for a smaller data set in central Manhattan. You can see this in this example. So the orange geometries would represent a section, the yellow geometry would represent an intersection, and the underlying traffic areas or auxiliary traffic areas would be linked to those sections and intersections, just as I explained in the beginning of the presentation. So this is what the resulting small dataset would look like, and we already transformed this to a CityGML 3.0 test dataset, so to say, and you can find this for download within the links I provided at the end of this presentation. We also had a look at the third dimension. There is a digital terrain model available, or a digital elevation model rather, and we used a small part of the model to adapt those objects according to the terrain. We incorporated hard break lines for the object boundaries, for example, sidewalks or traffic driving lanes, created a new digital elevation model from this, and then transferred this information into the individual semantic objects, thus lifting them into the third dimension. Now I want to show you some examples from this model. As I just said, the model contains many different objects such as roadbeds, intersections, sidewalks, plazas, parking lots, traffic islands, and so on. And each of these objects contains a number of attributes. So in this case, this surface is selected, and you can see that this belongs to Fifth Avenue. It has a certain function. One is for driving. There are 2 parking lanes in this surface, 3 travel lanes. The pavement rated everything was declared as good by the department. And this is all information contained within each traffic surface in this model. This would be a screenshot in central Manhattan. You can see here the Flatiron building. And if we zoom in, you can see that this information is also integrated for the building models. And this is a screenshot from the web map client, the 3D CityDB web map client I just showed to you. And you can select individual objects and directly get the information that is contained within these objects. This is the Flatiron building that has a certain height, a certain address, and so on. Yeah. Now let's have a look at the area directly in front of the Flatiron building. Here selected would be this roadbed object, which contains different information. It is part of East 23rd Street. It has 4 lanes. It has function 1 again, and so on. And this is true for all of these objects, for sidewalks, markings, and so on. This is the total amount of data that was produced from this and total amount of CityGML data. This is all available free for download on the project website. The links are within the presentation and also at the end of the presentation. You can see that this is quite some data. These are compressed zip files, and we created individual layers for roadbeds, sidewalks, and so on because of the sheer amount of data. These are the most important links. You can find the data for download here. There's a wiki page explaining in more detail the workflow, how we generated this model. On this GitHub page, you can find the FME workspaces, and there's also a YouTube channel which shows some demos and videos, which I want to also show you now. So this is now visualized in Google Earth with the KML files that were exported from the 3D City database. So the data was originally provided in CityGML and then exported to KML in order to be visible in Google Earth. This is a short overview on the detail. You can see individual curbs, sidewalks, plazas, the section areas that are independent of the roadbed, and each intersection area also contains multiple name attributes. So an intersection can belong to 5th Avenue and Broadway at the same time, for example. And I will show you a demonstration why this is useful in just a second. So to speed up the video a little bit, you can see here that all of these individual layers can be integrated within the web map client. So you can hide or unhide the individual objects. Now the parking surfaces will appear here shortly. The red surfaces are plazas, parking here, for example, and also the buildings can be introduced into the model. You can zoom in interactively, view this demo following the link that is provided in this presentation. So if you want to have a look at the demo yourself, you can do that. You can select the individual objects, scroll through the objects and see what attributes are contained. And of course, this is also possible for the street surfaces. This, for example, is a surface belonging to Broadway. The sidewalk next to it also has the information that this belongs to Broadway. It has information on its area and many more. So what can this be useful for? Let's have a look at the same scenario and do some queries with that. Since each object has a number of attributes, you can do some combined analysis with this. For example, you can first select all surfaces belong to 5th Avenue within this client. You can see here in yellow all the selected surfaces. And now you can see the intersections are not selected yet. So in this model, you would select an intersection. And since all the intersections also have the information which streets they belong to, you can now additionally find all the intersections that are belonging to 5th Avenue and select them too, which will be done now. And when you have selected all these areas, now you have all surfaces of roadbeds that are part of the 5th Avenue, and you could, for example, calculate the total area of 5th Avenue within this client. This might be one use case. Another one is many of these surfaces contain information on their condition on pavement rating, for example. So if you have the information on pavement rating, then you can do a query on all surfaces that have a low pavement rating. So the department provides information in New York with pavement ratings from 1 to 10, 1 with very bad condition of road surfaces, 10 with very good condition of a road surface. And I think 5 in this case was selected, and then you could make an aggregation on the total surfaces of transportation areas that have a not so good rating, and this could be used for estimating potential future repair costs of these surfaces, for example. Another application we tried, our chair developed a tool for calculating solar irradiation, which is mainly used for buildings. I think this was also done for the city of Helsinki. And we modified the street data in order to be usable for our tool. So we did a solar potential analysis, not only for the buildings in New York, which you can see here, with information on direct irradiation, diffuse irradiation for each month, and so on. And the buildings are textured to, according to these results. We also did this with the street space objects. So you could estimate local heat islands or find particularly shady places in New York City. And when we move a little bit through the model, you can see the results. And you can also explore this model interactively with the link provided. These were some of the demos for New York City, but I also want to show you that this was already possible for other cities. We did a very similar thing for the streets of Melbourne, where there's also a open data portal with many informations available. It was a very similar process to the model generated for New York City, but since the data was structured a little bit differently, different attributes were available, a different segregation method was chosen. We had to come up with entirely new FME workspaces, but had similar results. There was also data available in different levels of granularity, so to say. So for Melbourne, we made a model where sections are represented with just one object, since this information was available. But there was also information available for a model in a higher granularity where individual traffic areas can be represented. I just quickly want to show to you what this model for Melbourne looks like. Again, this is also accessible interactively with the links provided in this presentation. Another example is the city of Grafing near Munich, a small town. And we created a CityGML street space model for this from DWG drawing data, which was created by or gathered by the company 3D Mapping Solutions and is intended for creating OpenDrive data from it. And this also contained additional information, for example, on city furniture, on street signs, on vegetation, and also buildings with highly detailed textures. We also used, we had a master thesis at our chair for trying to coupling traffic simulations with street space models. And this was done for a model, the model in Grafing, for example. So from street aerial or linear street networks, a simulation graph was derived, which was used for the traffic simulation software Rissa. Then the simulation was conducted and the visualization result was played back again into the model. And I want to show you the results of this within this video. This is the model of Grafing with the street space models. You can see the visualization of the traffic simulation results. This was done because those traffic lights you can see here are not existing yet. So they simulated how traffic would behave there if those traffic lights would be integrated. And this street space model then can be used for a quick visualization of the results, for example. You can also see that there are signs, vegetation, buildings, and so on available in this model. This is a screenshot from the surfaces contained within the model, and this looks like one big object, but in reality, this is split into many different traffic areas, but all the traffic areas contain information to which lane they belong to. So if you're interested into getting the complete lane, then you can use, similar to the street name, the identifier of the individual lane to select each traffic area that belongs to an individual lane if you're interested in this for a specific purpose. And this is what is shown in this screenshot. Then one final example I want to show to you is the complex intersection in Ingolstadt, a town in Bavaria we did. And for this, we had OpenDrive data available. And I already talked a little bit of OpenDrive. This is a standard mainly used by several automobile companies. And in difference to CityGML, OpenDrive contains parametric representations of street space. This means there is a reference line available, and all information on different lanes is not represented with an aerial geometry, but with attributes basically saying the width of the street and so on. And at our chair, we created a converter from OpenDrive to CityGML called Airtron, which is an open source tool. You can access this via this link. There's also a GitHub page on this. And we tried this converter for this intersection in Ingolstadt, where we had this OpenDrive data available, and created a CityGML model from this. This is a screenshot of the result. You can see that this includes many different semantic informations on pedestrian crossings, on bike lanes, on individual driving lanes, on sidewalks, but also traffic signs are included in this data set, and markings also. I want to again show you a small video of this, what this looked like. Individual driving lanes can be selected, and they contain the information that there are a driving lane, and they also contain the information from which OpenDrive reference line they originate from. So it is possible to have a association between the aerial objects that are created in CityGML to the original parametric objects from OpenDrive. And as you can see here, since there were markings available, we created an independent marking layer, just as I mentioned in the conceptual part of this presentation before. So you can hide this layer if you want to, but also show it again. But the markings are independent of underlying traffic areas, since they can span over multiple traffic areas, and thus should be independent from them. We also used this model for a pedestrian simulation. There's a tool developed at our university called Momentum, which can simulate pedestrian movement. And as an original data to do this, it needs some kind of map with information on where pedestrians are most likely to walk, and areas where they are not allowed to walk, and with obstructions within the potential obstructions for pedestrians, for example. And since the CityGML model contained aerial information, for example, on sidewalks, on pedestrian crossings, but also on obstructions such as signs or vegetation, this data was used as input data for Momentum, and then based on this pedestrian traffic simulation was conducted. And again, you can find this model of Ingolstadt following the link provided in the presentation. I think I will provide most of the most important links also in the chat shortly, so this might be more convenient. Coming to the conclusion. First, I want to have a quick recap. I know this was quite a lot of input I presented to you, so I want to recap what I was trying to tell you or show you. I first started by introducing you street space modeling in general, why it is important with emerging applications and related standards that are already existent, and why we had a look at these standards in order to ensure interoperability of these standards with CityGML 3.0 transportation model. I then showed to you the different semantic, geometric, topologic concepts that are integrated into CityGML 3.0. I tried to show you the advantages of the appearance model that is a part of CityGML, how different transportation types can be integrated using CityGML, and how generics or application domain extensions could be useful for extending CityGML for concepts or applications that are not covered with this standard so far. Then I showed you different models and applications for detailed street space models. The quite big street space model of New York City, which was generated from open data, and some applications we already did with this model. The street space model of Melbourne, which was generated very similar to the model of New York. The street space model in Grafing near Munich, which was created from CAD drawing data. And the last model for Ingolstadt, which was created from OpenDrive data. So there are different ways to create street space model depending on the intended application and also the available data. And we did some tests for this, and I wanted to show you that these models already exist, and there are also some applications already tested for this. So in conclusion, there is an increasing relevance on semantic street space models. Highly detailed data is more and more available, for example, for mobile mapping systems, and emerging applications such as digitally testing autonomous driving systems or pedestrian simulations, as I just talked about, need this information. It is not enough to have this geometric street space information, but you need concepts on how to divide this or structure this in a semantic way, for example. And this is why CityGML 3.0 offers a revised and extended concepts on linear, aerial, but also volumetric representation using spaces, for example. Multiple levels of granularity are possible down to lane level accuracy. You can have a geometric and semantic segmentation using the section-intersection concept. And there are also new topologic concepts such as the predecessor-successor concept. I showed you some demos for New York City, Melbourne, and graphing. And I showed you how some applications already use, or some tests we did with this model for several applications. Finally, these are the links. I will provide the most important in the chat in a second. There are some very recent publications on this topic available from our chair, mainly those two here. The first explains the GML street space modeling in detail, also presenting the different standards and different concepts provided by different standards. And the second publication here from this year focuses on combined modeling of multiple transportation infrastructure, for example, a combined representation of road and railway infrastructures. There are some more interesting publications listed here. Okay, so thank you very much for your attention. And I'm very happy to answer your questions.
Thank you. That was very good one. I have a bit of echo, but hopefully it doesn't disturb that too much. We have a question about the New York City model, about the how does it kept up to date? There are
that's a very good question.
Updates, of course, in 5 years.
Yeah, that's a good question. I checked the Open Data portal, and until now there is no more recent data available. So, and even if when there will be new data available, it is a question if we can use the existing FME workflows one by one, because there might be a different structure of the data, might be different attributes available. So in the project, we showed that you can generate a CityGML street space data for an entire city as big as New York. Updating these models is, I think, also a question for digital twins in general. So this might be part of future research, and I think there has to be done a lot of work to the first step obviously is to create this model, but a very important next step is obviously to keep it up to date. And that's not something we have considered in this project yet.
Yes. So we have seen that FME is used quite a lot, and FME workflows are used quite a lot. So I assume that a lot of the effort goes to the actual workflow development. Yes. But how do you estimate the effort when thinking about the graphing city as an example? How many person months or how many weeks would it take?
That's a good question. So the source data for graphing was entirely different from the source data in New York, so it's quite difficult to compare those two things. I have a really hard time to tell you an exact number on this, to be honest.
Sure. Yeah, no problem. Good. Any more questions? Well, Jarmo is just telling that it was a great package, and thank you for this. And I think we can all join with that.
Yeah.
So we will share the presentations with the attendees, and it was a good attendance today. We had a lot of important contacts from both Helsinki and Tallinn side, and hopefully this gave you some idea also what might be the next steps in the development of the semantic model.
Thank you very much.
At this point, if there is any more questions, sorry. There is a question. I don't see anything here. Oh, it was in the chat. Let's see.
I just quickly provided the two most relevant links in the chat. The first is to the online demos I showed to you, and the second link is the information on the New York City model.
Okay, okay. One more question about the traffic model. Do you have any reference or experience in using street level point clouds? Like as an example, we have been using data provided by Cyclomedia.
Me personally, not, no.
Okay, okay, okay. But point clouds in general, of course, are quite
The data, the Open Drive data we used was derived from point clouds. So that's the workflow of the company 3D mapping solutions. They do mobile mapping, create detailed point clouds, and derive Open Drive data from this. So indirectly, but not directly with point clouds. No.
Right, right. Okay. Good. Any more questions? But we can, of course, also continue afterwards and so on. So at the moment, I would like to just thank you both for your presentation, and hopefully we can continue with the discussions in the future research and pilots as well, because that is what we are in here for. So thank you for all, and for the attendees, we will continue next week, and the theme will be energy, and also we will have a look at the Helsinki Energy ID extension and Helsinki Climate Atlas. But thank you for this one, and see you later.
Thank you very much.
Thank you.
Bye.
Bye.